In the past, power generating plants were only able to serve their local areas. Electricity didn't have far to travel between where it was created and where it was used. Since then, things have changed, and most of us get our electricity from the grid, huge interconnected areas of power producers and users. As power plants grew larger and further away from populated areas, the need for ways to efficiently move electricity over long distances has become more and more important. Stringing power lines across the landscape to connect cities to power plants may seem simple, but the engineering behind these electrical superhighways is more complicated and fascinating than you might think. Hey, I'm Grady, and this is Practical Engineering. On today's episode, we're talking about electrical transmission lines. This episode is sponsored by HelloFresh, America's most popular meal kit. More on that later. Generating lots of electricity is a major endeavor, often a complex industrial process that requires huge capital investments and ongoing costs for operation, maintenance, and fuel. Electrical utilities only earn revenue on the power that makes it to your meter. They aren't compensated for energy lost on the grid. So if we're going to go to the trouble of producing electricity, we want to make sure that as much of it as possible actually reaches the consumers for whom it's intended. The problem is that most power plants are usually located far away from populated areas for a variety of reasons. Land is cheaper in rural areas, many plants require large cooling ponds, and most people don't like to live near large industrial facilities. That means massive amounts of electricity need to be transported long distances from where it's created to where it's used. Power lines are the obvious solution to this problem, and sure enough, stringing wires, called conductors by power professionals, over vast expanses of rural countryside is in general how the bulk transport of electricity is carried out. But if we want that transport to be efficient, there's more to consider. Even good conductors like aluminum and copper have some resistance to the flow of electric current. You can even see this at home. We can measure a small drop in voltage when a hairdryer is plugged in directly to an outlet and turned on. Trying this again at the end of a long extension cord, the drop in voltage is much more significant. This difference in power represents energy lost as heat from the resistance of the extension cord. In fact, this lost power is pretty easy to calculate if you're willing to do a little bit of algebra, which I always am. Electrical power is the product of the current, that's the flow rate of electric charge, and the voltage, that's the difference in electric potential. For a simple conductor, we can use Ohm's law to show that the drop in voltage from one end of a wire to the other is equal to the current times the resistance of the wire measured in ohms. Substituting this relationship in, we find that the power loss is equal to the product of current squared and resistance. So if we want to reduce the losses in a power line, we have two variables to play with. We can reduce the resistance of the conductor by increasing its size or using a more conductive material, but look at what matters more, the I squared term. Reducing the current by half will cut the lost power to 1/4, and so on. Going back to Ohm's law, we can see that the only way to reduce the current and still get the same amount of power is to increase the voltage. So that's just what we do. Transformers at power plants boost the voltage up to 100,000 volts and sometimes much higher before sending electricity on its way over a transmission line. This lowers the current in the lines, reducing the wasted energy and making sure that as much power as possible makes it to the customers at the other end. This simple demonstration illustrates the concept. If I try to power a hairdryer using these thin wires, it's not going to work. The current required to power the dryer is just too high. It creates so much heat that the wires completely melt. That heat represents wasted energy. But if I first boost the voltage up using this transformer and then step it back down on the other side of the thin conductors, they have no problem carrying the power required to run the dryer. We've essentially swapped high current for high voltage, making the conductors more efficient at carrying power. What we've also done, though, is make things much more dangerous. You can think of voltage as electricity's desire to flow. High voltage means that the power really wants to move and will even flow through materials we normally consider non-conductive, like the air. The engineers designing high voltage transmission lines have to make sure the lines are safe from arcing and other dangers that come with high voltage. Most long distance power lines don't use insulation around the conductors themselves. Insulating in this way would have to be so thick it wouldn't be cost effective. Instead, most of the insulation comes from air gaps or simply spacing everything far enough apart. Transmission towers and pylons are really tall to prevent anyone or any vehicle on the ground from inadvertently getting close enough to the conductors to create an arc. Bulk electricity is transmitted in 3 phases, which is why you'll see most transmission conductors in groups of 3. Each phase is spaced far enough apart from the other 2 to avoid arcing between the phases. The conductors are connected to each tower through long insulators to keep enough distance between energized lines and grounded pylons. These insulators are normally made from ceramic discs so that if they get wet, electricity leakage has to take a much longer path to ground. These discs are somewhat standardized, so this is an easy way to get a rough guess of a transmission line's voltage. Just multiply the number of discs by 15. For example, this line near my house has 9 discs on each insulator, and I know it's a 138 kilovolt line. You'll also often see smaller conductors running along the top of transmission lines. These static or shield wires aren't carrying any current, they're there to protect the main conductors against lightning strikes. High voltage isn't the only challenge associated with electric transmission lines. Just selection of the conductors themselves is a careful balancing act between strength, resistance, and other factors. Transmission lines are so long that even a tiny change in the material or size of the conductors can have a major impact on the overall cost. Conductors are rated by how much current they can pass for a given rise in temperature. These lines can get really hot and sag during peak electricity demands, which can cause problems if tree branches are too close. Wind can also affect the conductors, causing oscillations that lead to damage or failure of the material. You'll often see these small devices called Stockbridge dampers to absorb some of that wind energy. High voltage transmission lines also generate magnetic fields that can induce currents in parallel conductors, like fences, and interfere with magnetic devices, so the height of the tower is sometimes set to minimize EMF at the edge of the right-of-way. In certain cases, engineers even need to consider the audible noise of the transmission lines to avoid disturbing nearby residents. Even with all those considerations, the classic model of the power grid, with generation far away from populated areas, is changing. The cost of solar panels continues to drop, making it easier and easier to produce some or all the electricity you use at your own house or business, and even export excess energy back into the grid. This type of local generation happens on the distribution side of the grid, often completely skipping large transmission lines. On the other side of the coin, the energy marketplace is changing as well, and grid operators are buying and selling electricity across great distances. Electrical transmission lines may seem simple, the equivalent of stretching an extension cord across the sky, but I hope this video helps show the fascinating complexity of even the seemingly innocuous part of our electrical grid. This is a segue between electrical infrastructure and my favorite meal delivery kit, HelloFresh. And this is my wife and I trying to film ourselves making dinner.
Shake that for us. Oh my.
Spending time in the kitchen is one of our favorite things to do together, and HelloFresh makes it super fun to cook and eat dinner together without the chore of planning meals and shopping for groceries.
Hey, get out of there.
The recipes are so delicious and always include seasonal ingredients that are different from the stuff we normally make.
Ooh, nice shallot stack, Grady.
HelloFresh comes right to your doorstep with fresh, pre-measured ingredients and easy-to-follow recipe cards, and it's flexible, so you can add extra meals, side items, or desserts to your order. Right now, the price starts at $5.66 per serving, which is pretty reasonable for a date night. And you know what's even more reasonable? The 8 free meals that HelloFresh is giving to fans of the channel who visit HelloFresh.com and enter Practical80 at checkout.
Can you bounce it off your arm?
That's $80 off your first month of HelloFresh. Just click the link in the description and use code Practical80 at checkout. Thank you for watching, and let me know what you think.